Today I'm going to talk about TCMalloc hot and cold feature. It's a new feature in this memory manager. But to warm up, let's talk about me, about my conference talks, previous conference talks. So in 2020, I gave talk about dress sanitizer anatomy. In 2021, I gave this same talk, but about thread sanitizer. In 2022, I gave talk about Go and how to use it without runtime. In 2024, I gave a lot of talks. So first of these talks was about leak sanitizer and memory management. Second was about sanitizers and linker tricks, how sanitizers uses some linker options to create interceptors, to intercept the system calls. And I think the final talk on this year was about leak sanitizer and address sanitizer tips, tricks, and hacks. I gave this talk on CPP London. Unfortunately, recording is not available, but you can download slides from this QR code. And this year, I've presented memory profiling techniques and LLVM MemProf tool on CPP Russia 2025. So all my talks are about system programming. Most of my talks are about memory and memory safety. But today, I will talk about memory performance. So some of my previous talks are connected with this one, but the most relevant is the last one. So this here talk. Okay, now let's talk about memory managers. To use memory, usually, not always, but usually we want to allocate it first, right? And to do it, we are using memory managers. And there are many different memory managers. We have to compare them somehow. That's why there are a lot of different benchmarks for memory managers. And the majority of benchmarks actually compares memory managers by allocation speed or deallocation speed, how fast memory manager can allocate memory for you and deallocate it later. Also, sometimes they are comparing memory managers by memory fragmentation and size overhead. Okay, so basically, these benchmarks compares memory managers by checking how memory managers implement these two lines of code. So, but usually, memory allocation is not a final goal in your application. Usually, you want to use somehow this memory. So we are allocating memory to use it, to write something to this memory and read it back later. So let's add missing line of code here. This is our application. And actually, this line of code is deserved to be optimized because memory access speed is very, very important for your whole application performance. And hopefully, our sometimes memory managers able to help us to optimize this line of code. Now, let's talk about just one memory manager. So it is TCMalloc. And actually, it is not just one memory manager. There are at least two of them. One of them is a part of gperf tools. It is located here on GitHub repository. So it's open source. And another is internal Google TCMalloc, which is open source too. And it lives in another GitHub repository. Actually, this TCMalloc, internal Google TCMalloc, has some interesting traits. So first of all, it has a lot of additional optimizations for multi-threading applications. It's better fine-tuned for high performance. Another trait that it has additional dependency from absolute library, and also you have to use Bazel to build it instead of CMake. So, and in 2021, Google added new feature to their internal TCMalloc. They added hot-cold hinting for allocations. So, this hinting is actually a user-provided prediction how frequently this allocation will be used. So, used, accessed, read-write operations. So, and this is a piece of documentation for this feature. So, and you can see that TCMalloc provides a hot-cold variant that application may use to provide hints as to how frequently an allocation would be accessed. By specifying hot and cold hints, TCMalloc may separate allocations to improve data locality for hot heap. Okay, so in practice, for you as user, programmer, it means the following. They have added two additional, I'm sorry, not two, one. Additional operator new variant. So they have added additional parameter to this operator. So this is hot-cold parameter, and the value of this parameter has a range from 0 up to 255. 0 for less frequent access, and 255 for most frequent. So this is a usage example, how you can allocate memory. Here we are allocating just integer in heap, and we say TCMalloc that we will use this memory very, very rare. So this should be a cold memory. So it is our prediction. For sure, we later can we can frequently access this integer, but in this case, you can expect some performance degradation. Because, so it's better to not break this contract later. Okay, now let's talk about connection this feature with LLVM MemProf tool. So this is two different changes in two different repositories, and what is common here? It seems like these changes in TCMalloc and in LLVM repository are parts of a bigger and more ambitious project. It is PGO to improve heap access speed. So PGO is profile guided optimization. On October 2020, Teresa Johnson have committed the following change to LLVM repository. So she added runtime support for the memory profiling. And in the description of this change, you can see that profile information will be used to guide compiler, optimizer, and allocation runtime to lay out heap objects with improved spatial locality. Okay, so the final goal is PGO, and the usage of this feature when it will be stabilized will be the following. You build your application with fMemory profile option. You run your application with realistic data or workload. It generates a memory profile file with some statistics how your application used each allocation during the run. And this is just an example of one allocation statistics from this profile. You can see that we have here stack trace. Stack trace is just is unique for each allocation. And we have count and size statistics. So allocation count, it's how the total count, how many such allocations was done during program run, program execution. And size statistics, because the same allocation could allocate different memory size. For example, if you are allocating arrays. Access count, so it is, again, statistics, how frequently allocated memory was used. Used means read-write operations. Lifetime in seconds, so this application was very fast, and that's why we have zeros here. But this lifetime is in seconds. And CPU stats. So for memory managers, it is very important to check if there were such events as when you allocate memory on one CPU and deallocate memory on another CPU. So it's like migration, memory migration from one CPU to another. And yeah, and also we have access histogram per 8 bytes. You can see that this allocation size was 24 bytes. Actually, it was a very simple structure with only 3 fields. Each field was 8 bytes long. And here you can see that first field was accessed most frequently, and last 2 was infrequently used. Okay, what next? Next, as usual with PGO, you just build your application with option of memory profile use, and you link your application with this Google TCMalloc with this feature. And compiler will automatically replace your simple, not hinted new operators by new operators with hot-cold value. The values for each operator will be calculated automatically from profile statistics. And also, compiler is able to create some function duplicates if there are hot used allocations and cold used allocations that shares the same path, the same pieces of stack trace. And please note, so hot and cold usages is not about how frequently you allocate something. It's how frequently you access it. It's very different things. Okay, so more details about this LLVM MemProf feature you can check in my previous talk. This talk was in Russian, in C++ Russia 2025. You can scan QR code and watch it. But the short summary, which was 7 months ago, MemProf tool is very cool feature. This PGO optimization is very cool feature, but unfortunately, it is not so stable. It is not for production yet. So you can try to use it for your pet projects, or even can try for your production code, but there is no guarantee that it will work for you now. So, but TCMalloc hot-cold hints feature is ready to use in internal Google TCMalloc. Now let's talk about our intuition and about our expectations from this feature. So for our default operator new calls, we are not expecting any degradation. Okay, we change nothing, we just using TCMalloc, so we don't expect any degradations at all here, both for allocation speed and for access speed. For hot marked objects, we are also not expecting any degradation, but we can expect some performance gain in terms of accesses. And for cold marked objects, we can expect some performance degradation, at least for access speed. Actually, the first, not hinted new operator, it is the same as hot hinted. So in current TCMalloc implementation, they considered all memory as hot by default. So the only thing what you can change, you can mark some objects as cold. And that's it. But it is current implementation. It could be changed in future. So now let's talk about implementation ideas, how it could be implemented. So the main idea is to keep hot and cold objects separately. So just do not, as in some kind of dedicated memory pools areas, by separating by addresses anyways. Just don't keep cold next to hot. So it sounds very logical, but why should it work? Maybe we will have better swap usage, right? Yes, we will. So why? Because in memory, in operation system, memory is divided in 2 pages, and typical size is 4 kilobytes, but could be up to 2 megabytes or even more. And one page can have several allocated chunks. Operation system tracks access frequency to the pages, and in case of RAM shortage, it swaps, and swap means it removes this page from RAM and puts it to the disk, so it is very slow operation. And it swaps the least used pages, so the most infrequent accessed pages. And if a page was swapped, if there is access request to the memory from this page, it will bring it back to RAM. So it is, again, very slow operation because it have to read it from disk, load into RAM, etc., etc. So very, very slow. And if you have mixed usages on of the same page, like here, operation system, so such events when operation system have to write to the disk, read from the disk, swap it back, so will be very frequently. And if we are separating hot from cold, some pages will be only hot and will remain in the main memory in RAM longer. And cold pages could be safely swapped to the disk. So for sure, hot-cold separation will improve swap efficiency. Yeah, so that's great, but I think not each Linux system use swap. So it's maybe not the main purpose, maybe not the main use case. What else? Maybe we will be able to find some additional source of speedup. Maybe we will have a better cache utilization, L1, L2, or L3. Partially, because cache line is typically 64 bytes, typically, not always, not on all systems, but typically it is 64. And TCMalloc tries to not allocate 2 objects on the same 64 bytes to prevent false sharing between allocated chunks. So we will for sure have some cache benefits if in case of prefetching, but not because one memory request brings more than one object to the cache. And the major performance gain source lies on another cache in TLB. Actually, here we will have data TLB. So TLB is translation look-aside buffer. So it's simply a cache which stores recent translation of virtual addresses to physical addresses. So it is a piece of hardware. So it's a piece of MMU, which itself is a piece of CPU. So this cache is not in your some main memory. It is just a separate piece of hardware. Okay, so let's go by example. So we have our famous application. So we are dereferencing P and want to write to this integer 42 number. So how to do this? For do this, we have to find physical address for this pointer, and this pointer contains actually virtual address of this memory cell. So this is our pointer. This is our virtual address space divided into pages, and this is one page. Content of our pointer, this address could be separated into two parts. So it is oversimplification, but it is enough for this talk. So the least significant 12 bytes, it is offset, and the most significant bytes is a page number. And page number helps us to find a page for our memory cell, and offset helps us to find our object inside the page. Okay, but how to find physical address? Because we have to write this to real memory. Operation system uses page tables. Actually, usually they are using page table hierarchy, but for the sake of simplicity, we will use just one here. So, and real physical memory is divided into frames. And each frame is just like page, so usually the same size, 4 kilobytes in this case. So, and we are doing very simple thing. We are replacing page number by frame number, and frame number could be found in page table. By frame number, we can find a given frame for our piece of memory, and offset will remain the same as it was for page. So actually, this address translation is just replacing page number bits in our pointer by frame number bits, and that's it. Very simple thing, works perfectly, but very slow. Because page table is pretty big table, a lot of data, and it's stored in your main memory, in RAM. So to access memory, you have to access memory. So it will add several memory accesses for each memory access. So that's why it could be very, very slow. So as usual, this issue was solved by adding cache. So it is our TLB. This is very small cache, but very, very fast. And first call will be slow as usual because there is no entry for our page number in this cache. That's why we will have to use page table. But the second call will be very fast because we will not have to do additional memory access. So we don't need page table at all. So that's why it will be very, very fast. But TLB is very limited resource. That's why it is very important to minimize diversity of page numbers during the same time frame. Okay. Because one page or frame can have several allocated chunks, they will share the same TLB entry. And if we have mixed usages of the same page, some Memory is rarely accessed, some is frequently. TLB usage will be inefficient. So this is an example of bad page because we have mixed usages. So some objects are hot, some are cold. Also, we have not allocated memory here, so never accessed memory. This is example of a good page. And this is a good page too, where we have only cold objects and not allocated memory. OK. Both effects, TLB utilization and swapping, become more visible in case of using huge pages. Because in this case, more objects will sit on the same page. To help operation system swap cold pages efficiently, we can keep use small pages for cold memory allocations. So it will help operation system smoothly swap it. And we can use huge pages for hot objects. OK, so now let's talk about implementation, how it was implemented in TCMalloc. So a short helicopter view to TCMalloc internals. And actually, TCMalloc generally is just very sophisticated cache hierarchy. So very smart, very sophisticated, but it's just a cache hierarchy. So if your user code wants more memory, it will call front end, and front end is just a per CPU cache. If per CPU cache doesn't have a suitable chunk of memory for you, it will try to get it from middle end, from transfer cache. If even transfer cache doesn't have the suitable memory chunk, it will request backend to refill center of free list. And so backend is huge page aware page heap, and it can request memory from operation system. And main implementation of hot cold feature is here. Because all other levels, I mean front end, middle end, is just very sophisticated lists of pointers. But huge page aware page heap decides where the actual memory will be located, actual addresses of memory. So that's why on this level, we can decide to separate one type of memory from another type, from hot from cold. OK, so what huge page aware page heap does for us, for this feature? So it separates address spaces, arenas by memory type, actually by memory tag. So it is a piece of source code of TCMalloc. And you can see here a lot of different tags. But the two most important tags for us is this. So it's knormal and kcold. Kcold. As you can see, there is no special tag for hot objects, for hot memory. You can be only normal or cold, and that's it. OK. And how this tag is being used? So this tag actually is stored just inside of values of your pointers, inside addresses. So there are 3 dedicated bits in your address. So it's from 42 up to 45 positions in a pointer. So I've highlighted it by green here. So for hot, normal addresses, and for cold addresses. For hot addresses, we have value 4. And for cold addresses, we have value 2. So, and actually, you can get value of your pointer and extract this tag if you are using TCMalloc, and understand what the memory type and how this memory was allocated. And just an important note, this tag is very different thing from 6-bit tag on LLVM U57 mask format. So this 6-bit tags resides in 57 up to 62 bits in your pointer on the top byte of 64 pointer. So it's different things. So now you can see why in TCMalloc implementation, normal or hot objects will be never next to cold objects, because we have just very different values here. So, and the second thing which huge pair-aware page heap does, it advises operation system to not use huge pages for cold allocations. So for cold allocations, it will use always, so okay, not always, but mostly small pages, for 4 kilobyte pages. Now, let's talk about benchmarks, because all this theory is very interesting, but what about numbers? Unfortunately, I didn't find any published benchmarks for this feature, so I've created my own. So my benchmark is very simple, but we have to start from something. So my benchmark creates 16 million objects of 64 bytes each. It randomly marked, so these allocations randomly marked as hot or cold. And hot objects are linked into ringed list. So this linked list could be created sequentially or randomly. So, and access pattern to these objects, hot objects. So we will access hot objects only. So we will not touch any cold objects. So access pattern is very simple. We just go through this linked list and we will write payload field, and that's it. So very, very, very simple. So, and on this benchmark, we will have 4 different setups. For each page size, for 4K pages and huge pages, and for randomly created list and sequentially created list. So 4 different setups. And for each of these combinations, we will use 7 different hot objects percentage, from 0.1% up to 99.9%. And also, we will have 3 different hot hinting settings. First is correct, when hot objects marked as hot, cold as cold. Default, so it's just default behavior when we are not separating hot from cold. So both pools will be marked as hot. And inverted, when hot objects marked as cold and cold marked as hot. So let's break the things. And in total, we will have 84 benchmark runs. OK, now let's talk about results. This is results for 4K pages and a random list. But first of all, I have to present this chart type. So because axes are very important to interpret the results. So vertical axis is time in milliseconds. You can see that we have something about 15 seconds here. And horizontal axis is hot objects percentage from 0.1 up to 99.9. So, and you can see that if we have a number of hot objects less than 9%, we will have significant speed up for correct or inverted hot hinting settings. So the actual speed up could be seen even clearly on this chart. So this is performance gain chart again. vertical axis is speed up in percentage, and baseline is our default settings when we are not separating hot from cold. Horizontal axis as usual. So, and you can see that we have significant speed up. So up to, I think, 50% for 0.1 percentage. For both correct and inverted. So for small pages, random access, it even doesn't matter how we marked hot and cold objects. Correctly, when hot is hot, cold is cold, or invertedly, when cold is hot and hot is cold. So, interesting. And this chart for the same setup shows us DTLB store misses. So, vertical axis is DTLB store misses percentage. DTLB store misses, it's when we want to write something to the main memory, and during physical virtual address mapping to physical address mapping, there is no such entry in DTLB. So it's a DTLB miss. So, and it has a range from 0 up to 100%. Horizontal axis as usual. And you can see that for a lower hot objects percentage, we can significantly decrease number of DTLB store misses. For 1%, it's, I think, 40% better. And for 0.1% of hot objects, it will just eliminate these DTLB store misses at all. Now, let's talk about sequential access. And here we have something new. We have significant performance degradation for default settings when hot objects are rare. So I mean less than 50%. Why? Because in this case, sequential access starts to be similar to random access, because we will have a huge gaps between hot objects. And you can compare the speed of sequential access and random access on this chart. And you can see that we have very similar numbers here for 0.1, similar here, and now it will diverge. So, and what about speed up? Speed up is actually huge. If we are separating hot from cold, we will have up to 80% speed up for hot objects. And again, it doesn't matter how we marked them, so correctly or invertedly. Yes. And what about DTLB store misses? Yeah, so you can see for default settings, we will have a lot of DTLB misses when hot objects percentage is low, but after that it will disappear. And if we are using correct or inverted, if we are separating hot from cold, it will just eliminate the DTLB store misses at all. Okay, now let's try the same for huge pages. So it is random list, and we have something new here. We have performance degradation for inverted settings. So, and this performance degradation is something about 20%. So if you accidentally marked a hot object as cold, then you will have performance penalty. But correct settings still have some speed up improvement. So up to 20% for 0.1 hot objects percentage. And even inverted setting will give us a little improvement here. But for sure, on higher hot objects percentage, it will give us penalty instead of gain. Okay, so if you're comparing our speed up here for correct setting with speed up for small pages, you can notice that this speed up is not so great. Why? Because default setting itself, without separating hot from cold, works much better in case of huge pages, because we have less number of pages and we will have less DTLB store misses. You can compare default for kilobyte, it's blue, with default huge, it's red, and you can see that we have something around 20% speed up just by using huge pages. And it is DTLB store misses, and you can see why inverted is so slow. Because for cold objects, TCMalloc always tries to use small pages. That's why we have a lot of DTLB store misses, and that's why inverted is so slow. Okay, huge pages sequential access. So the picture is very, very similar to the picture of small pages sequential access. But actually, we have something unexpected here, because correct and inverted is very similar. So even with huge pages, it seems like even if we are using small pages for cold objects, so this penalty is much less than benefits of just separating hot from cold, used and unused objects for sequential access. You can try to find some trends here for huge pages, sequential access, DTLB store misses, but what is important? Actually, here there is only zeros, because the value for DTLB store misses is this. So it's less than 0.02%. So this DTLB store misses rate will not affect application performance at all. And all results, benchmark results on the same page. You can check it later, so slides are available. And now, if you want to use this feature, but you cannot use Google internal TCMalloc, actually, there are a few options to do it. So, several options. First, you can create your own allocator backed by a map with MetaDevice. But actually, I cannot recommend it because it could be hard and error-prone. And also, actually, you could lose performance instead of gaining it. It is very complicated, and you can bring some additional vulnerabilities to your application. Another option, you can try to adjust your existing memory manager. If you are using Eclipse, you're unlucky, you cannot. If you are using CMalloc, actually you can, because it has an API to use your own arena and use it for some allocations. So you're lucky, but you're not, because CMalloc is dead. There is, I just found actually another promising memory manager. It is MemProf. Maybe it's not so famous, but it has rich API. It's alive. I think this MemProf is backed by Microsoft now. You can create and use separate arenas for call allocations. But if MemProf is not a case for you, then I have several other options, even with Eclipse. If you're not caring about swap efficiency, so you don't have to build your allocator from scratch, from map level. So you can use memory which was allocated by your current memory manager. There are two general strategies here. First, you can create memory pool for cold objects. So usually, you don't want frequently create and destroy cold objects. Usually, it creates rarely, destroys rarely, and accessed rarely. That's why you don't have very carefully optimize allocation speed for it. It could be slow, but reliable. So reliability is very important thing. So, and you can create cold memory allocator backed by memory allocated by memory manager. So this is one strategy. Another strategy is memory pool for hot objects. So all objects could be considered cold, except specially marked as hot objects. And sometimes it could be beneficial to copy data from your cold memory to hot memory pool, process it, and if we have some results or updates for these objects, to write it back to cold memory after processing. For sure, don't forget, and you can combine these two strategies on your application. And don't forget to benchmark it, because your decisions should be based on numbers. And don't forget to care about DTLB usage efficiency. Now you know how it affects the whole performance. You can get up to 50% performance gain. So thank you. Don't forget to feedback me here. And here you can get additional materials to this talk. So with source code, benchmark source code, and with raw numbers for these statistics. And also there are two different files for this presentation on GitHub. So you can download slides.
Thank you, Alexei, for the hot talk about memory allocation. I was working on a project where we had our own allocator. Of course, every C++ developer has to develop their own, and it was replaced with TCMalloc successfully. So you can ask questions in English. That would be great. Let's start with the guy in the T-shirt of unknown color.
In Russian too.
Thank you for your talk. I have a question about security, because I have a feeling that this allocation could be used to leak some secret info, because there is difference in access time to hot and cold object. Is it not founded, or is it some recommendations how to use this allocation to not leak info?
I think you will have different access speed even without this TCMalloc feature. Because if you rarely access some memory, then you will have DTLB store misses or load misses. And also your page could be swapped. And in this case, you will have a huge time to access this piece of memory. So I think it's nothing special here. And another thing that modern memory managers are separating memory by size. So that's why it will also affect access times. So.
Thank you.
Так, кто еще не сделал, пожалуйста, оцените доклад. Для этого есть QR-код. Да.
QR-код, вон он, там он, справа внизу. Да.
Thank you for your talk. As I got it, you said we can set value from 0 to 255 as a hint, then TCMalloc converted to one of two flags. with values 2 or 4, and then uses 3 bits in pointer.
Yeah.
First question, why it's needed 3 bits to values? And second question, what if we set not values 0 or 255 in hint, or something in middle of range?
Yeah, so first, these 3 bits are used for tag value. And tag value, you can see that in enum class, which I showed, there are more values here. So all these values are stored in these 3 bits. So it's one part of the question. Another part is what will be used if you are choosing something in the middle, from 0 up to 255. Actually, nearly nothing. So it's have some kind of threshold. I don't remember exactly, maybe 1 or 10. It just now tries to separate hot from cold. If you if your value is bigger than this threshold, it will be considered as hot, and you will have this tag value. And if it's lower, it will consider it as cold, and that's it. So I think they made this API with this range just for the future. Now, actually, it is just 0 or 1.
And in the future, they will need to use more bits from pointer.
I don't know its implementation details.
Yes, but
maybe
we can't convert 255 values.
I don't know.
Так, кажется, микрофон не работает. Должна зелененькая гореть.
Earlier in TCMalloc documentation, they said that TCMalloc never turns memory pages to the operating system. Do you know if this is still the case?
Never back to
the operating system.
I don't know.
Okay.
As far as I remember, it can actually, because I saw something in their source code.
Thanks a lot. By the way, I'm not sure. Did you mention or not about the initialization of variables and retexts? Did you have a difference between when you create a variable for your benchmark to measure, and when you check the retexts?
I check actually right access, but anyways. Initialization, so like preheating hot objects, was done in separate loop before benchmark.
Okay, so as I understand, we have predictable cache behavior.
Yes, somehow, because in case of random access, all this data cannot be stored in cache, so because cache is too small.
No, I mean, for example, could we face with memory barriers in this case?
In my benchmark, so it's single-threaded application.
Got it.
Спасибо. Вот еще вопрос молодого человека сзади.
Thank you for the talk. My question is, do you name applications or classes of applications that would benefit of this kind of optimization? Because now we see only on synthetic tests, and it's hard to have any intuition of how my application mixes cold and hot memory.
You have to try. So actually, that's why Google works on PGO for it, because it's hard to understand which allocation should be hot and cold without this profiling information, without this memory profile. That's why they are trying to make it automatically. You just turn on this compiler feature, run your application with realistic payload, and it will generate values for hot and cold allocations
Is it possible to predict speed up of the application just by measuring without modifying the application? I mean, do I need to implement it and then measure by myself, or?
Yeah. So actually, you can try now. You can try to build your application by clan with these LLVM features of MemProf. You can gather statistics and read it by your eyes. So because it's in human readable format. As it was shown on my slide with, yellow square. And you can analyze your code after that and manually mark your allocation as hot and cold. So I think the rule of thumb here is if you have small set of objects which are very frequently used, you can mark it as hot, and all other objects could be marked as cold.
Okay, thank you.
Спасибо. Так, давайте последний, наверное, вопрос, да?
Yeah.
Да, пожалуйста.
So, if, like in my applications, I usually don't have objects that are accessed frequently and less frequently. It's more like you have an array, and part of an array is accessed frequently, and the other part of the array is accessed infrequently. So does it pay off to split the array into two pieces, the hot and cold piece, and then dynamically dispatch between, and benefit of cache usage, or not?
I think yes. So at least you have to consider an option to have hot objects from this array on the same page or on the smaller set of pages. So you can do it by different ways. They could be in the same array, but hot objects could be compacted to the sequential indexes. So, and cold objects should be somewhere else. Yeah.